Okay, everyone, let's get started. Sorry, I got a cold from my daughter, so my voice could be a little bit soft. Um, so I also posted homework 4 last Wednesday, and if I have time, I will give some hints on homework 4 at the end of today's lecture. There are some stuff we need to cover first before you will be able to finish homework 4, and if not, I'll talk about more about homework 4 on Wednesday's class. You can start working on that very soon. So we're going to continue with this twin wave theory we introduced at the end of the last lecture. And this is probably the last calculational technique we're going to learn that is kind of analytical. And later on, we're more going to deal with sort of numerical techniques in dealing with many-body systems. And last time we talked about the ferromagnetic high-split chain. Today's focus will be the anti-ferromagnetic high-split chain. And we're trying to get analytical solutions of this Hamiltonian with this mapping to bosons, and also with this approximation called spin wave approximation. So we'll review those just in a second. So first, let's write the Hamiltonian down. So the Hamiltonian is given by just SI dot SI plus 1. So these are the vector dot product of the spin angular momentum. You can also write it in the component form. So it's SIX, SI plus 1x, plus SIY, SI plus 1y, plus SIZ, SI plus 1z. So it goes like this. And then the sign in front of these terms are positive, which denotes the anti-ferromagnetic coupling. So that means for a nearest neighbor term, for any of those terms there, if you want to minimize the energy, you have to have the two spin angular momentum anti-aligned in order to get a -1 of the product of those two spin operators. And we also talk about it's impossible to minimize all three terms just because they don't commute. So so how are we going to deal with this model? The first trick we're going to do is to sort of first assume what the ground state will look like. It's going to be assumption only because we don't know the exact ground state. It's going to be complicated as we talked about previously. But to start doing these sort of mapping to bosons, we have to first define a vacuum, right? So it's like, what is a state that corresponds to the vacuum? In the ferromagnetic case, it's easy because we know the ground state is just all the spins polarized in some direction, and then we can just call that direction the z direction. You can just define the axis in that way. And then the ground state will basically be all the spins polarized in z, and you can treat that as a vacuum state for the bosons. So the mapping between the spin and the bosons, we talked about this last time. So this is called the Host and Primakov transformation. So this transformation basically says the SZ is going to be mapped to A dagger A minus S, where A is the creation operator, creation annihilation operator of a boson. And this basically means the SZ equals to minus S, which is the spin pointing down in the Z, gets mapped to the state with 0 bosons in it. So if you just look at that expression, then every time you apply the raising operator for the spin angular momentum, it will be close to basically the creation operator because you're basically adding one boson to the system if you are increasing the spin angular momentum in Z by a unit of h bar. But the correction is that we have to have this 2s minus a dagger a in the square root. That is to make sure that if you already have sz equals to plus s, you can't actually raise the spin angular momentum any further. So that square root makes sure that in the corresponding bosonic case, when the number of particles is equal to 2s, then you can't actually increase it anymore. So the sz equals to plus s will correspond to the state with 2s particle. Since s is going to be an integer or half integer, so 2s is always an integer. So that goes, so it's always an integer. And similarly, s minus is just the Hermitian conjugate of the above equation. So I'm just going to flip the order as what we do for the Hermitian conjugate of a product of two operators. And the square root also makes sure the angular momentum matrix elements are correct. So that's a mapping we introduced. So in the ferromagnetic case, we basically just assume this is going to be, S equals to minus, this is my ground state, and then I'm going to look at the low energy state, which are not going to be very different from the ground state. In this case, the A dagger A is going to be small because we're kind of close to the ground state. The ground state has A dagger A equals to 0. So this is going to be much, much smaller than 1. In this case, we can actually approximate those by just A dagger. And, sorry, this is A. NA. The SC, you can still keep it in that way. So you can do this approximation. And that's going to greatly simplify this because, if you look at the Hamiltonian, you got the x, x, y, y. And that actually just becomes S plus, S minus. And then we solve that. We basically just get a very simple cosine energy spectrum, similar to the tight binding model for non-interacting particles. So in this case, it's actually going to be a little bit more complicated because the ground state is not going to be all spins polarized in Z. So you can't actually, use this mapping in this way. And what we're going to assume is that the ground state is going to be a Neal order state. Is Neal order. This Neal order has an accent on this letter E here. So what it means is I'm going to assume the ground state goes like this. So it's an antiferromagnetic state. So this is in the Z direction. So this is in the Z direction. So spin is like up in Z, down in Z, up in Z, down in Z. So of course we know that the actual ground state is not this, but we're going to make this assumption just to make sure we can get started. And then we can see that by doing this, by assuming this ground state and also assume that the real ground state is not that different from this state, we're going to check whether this whole spin wave, approximation makes sense. So we're going to first do assumption and then later verify whether that assumption actually makes sense. Okay, so so with this, we can actually, change the Hamiltonian a little bit. So this state is kind of hard to deal with because it depends on the even and odd number of sides. The even sides have spin up and the side have spin down, and the odd side have even spin up. And we can actually do a basis transformation. So we're just going to set the odd sides. So these sides, we're going to basically redefine the z-axis. So we're going to flip the x and z component of the spin angular momentum. So we're going to change that to minus I, SI, XC. So this is the basis transformation. As we said before, you can only flip two directions of this two spin angular momentum. You can't flip just one or flip three. So here I'm flipping two directions of the angular momentum. What I really care is the z direction. And if I do that, then basically the odd sides get a -1, so the up actually becomes down. So after this transformation, my ground state actually looks the same as the ferromagnetic case. Basically, that is going to be my ground state. So all the spins pointing down. So that simplifies the problem. But of course, there's a price you have to pay because if you look at here, then because the x interaction picks a minus sign only on the odd sides, then this Hamiltonian needs to be changed. So the Hamiltonian actually will acquire a minus sign in the xx interaction. So and also the zz interaction. So this is si x si plus 1x plus si y si plus 1y minus si z si plus 1z. Because of this -1 to the I. For even one, the -1, to an even power is 1. But for odd one, it gives you -1. And if you look at the interaction in x and y, they're always between an odd side and an even side, so they always pick a -1. And similar for the z direction. So both of those will get a minus sign. So this Hamiltonian actually looks different from the ferromagnetic case, where you still have this ground state to start with, but all the signs are positive. So that's the main difference. So now we can still do this mapping here. We can use these two mapping equations. It's relatively simple because you don't need to worry about those sort of phase operators in the Jordan-Wegener. You basically just change s to a dagger, s plus to a dagger, and s to a. And here this is xx and yy, so you have to first write it in terms of the plus and minus. We can use this equation we talk about. So this is sx is basically 1/2 of si plus si minus, and siy is equal to 1/2 of si plus minus si minus with a 2i. And that you can get it from the definition of the si plus and si minus. So it's given by this. Plus or minus just x plus or minus iy. So then you can basically plug this in. So the algebra is relatively simple. So if you do that, what you're going to get is minus 1/2. Then you have si plus 1/2 plus si minus, si plus 1 minus, and then you still have the z term as before. So compared to the ferromagnetic case, this term actually looks like a plus minus and a minus plus. where you can replace it by, A dagger A, right? And here we actually get the pair, raising and pair lowering operators, which is going to, it gets mapped to the pair creation and pair annihilation. And the next part with the spin wave approximation, so this is approximation. So then this just becomes A dagger and A dagger. And then here we have the A and A. And then we also have the Z term. So the Z term, we're going to treat it similarly as what we did before. So each of the SZ just gets mapped to A dagger A minus S. So this becomes A dagger A dagger. So A dagger I AI minus S times A plus 1 dagger AI plus 1 minus S. So that's just how we map the SZ to A. So we're going to simplify this a little bit. So for this last term here, we also said that the dagger AI is still going to be a very small quantity. So the quadratic term is going to go away. And we're only going to keep the linear term in AI dagger AI in that expansion for the last term. So for this term, it's a product of these two. So we can forget about the quadratic term because AI dagger AI is already small. So if you do that, this last term here just becomes 2S times AI dagger AI. And first of all, it should be S times AI dagger AI and S times AI dagger I plus 1 and AI plus 1. But because the sum is over all the i's, so the sum over I plus 1 as a sub-index is the same as the sum over I. Because it's a dummy variable, it's summed over. So I'm just going to simplify this to this. And this is also, we are also assuming periodic boundary conditions, so you can see the I goes to n. So that allows us to do the discrete Fourier transformation later. So the only trouble here is that we have these pair creation and annihilation term here. This Hamiltonian is quadratic. The only trouble is the pair creation and annihilation. But that we know how to deal with because we can use the Bogdanov transformation to get rid of those. So this is more complicated than the ferromagnetic case, but still something we can deal with. So still the usual trick. So first we're going to transform to the momentum space. So we're going to introduce the transformation to go to the momentum space. And in your homework 5, there will be an exercise problem, so you can sort of practice this whole calculation yourself. And it's going to be a more or less direct generalization of what I'm doing here. So that's basically the transformation from the AIs to CKs. CKs are the creation and annihilation operators in the momentum space. Because the system is translation invariant, we can always introduce momentum as a good quantum number. So if we do that, so the Hamiltonian is going to be changed to this. I think I'm also forgetting S here. So let's see. So when you do this transformation, I think you're actually going to get, well, this is not 1/2 but S, right? Because there's actually, there's a 2S here. So actually this is wrong. So there's a 2S here. Square root of PS. I'm forgetting about a constant factor because I'm only dropping A dagger A. So this is the correct one. So after the transformation to the momentum space, it looks like this. 2 times ck dagger ck minus cosine 2 pi k over n, and then you have ck cn minus k plus ck dagger, the Hermitian conjugate of this. So it's cn minus k dagger, ck dagger. And then with some constant, I'm also dropping here. So there's a constant here, which is because of this s squared term in the expansion. So this term, the first term is pretty good. It's already diagonal, but these terms are not. And the Cn minus k is the same as C minus k because the system is periodic. And then we have to do the Bogdanov transformation. So the Cn minus k is the same as C minus k. And then we can introduce these bk's. So this is very similar to what we did in the weakly interacting boson case. But this is the reason why we have to do all those Bogdanov transformations. It's actually useful in multiple different cases. And to diagonalize this, we also have to set tanh 2 theta k, in this case, to be equal to basically this, this coefficient. So it's equal to minus cosine 2 pi k over n. So once you set these Bogdanov angles correctly, you can diagonalize this Hamiltonian into a nice form. That's always what we're trying to achieve. So you get to something like an epsilon k bk dagger bk, plus some constant you don't care about. And then in this case, epsilon k you can explicitly find. So it's equal to 1 minus cosine square 2 pi k over n. And this you can also simplify this because it's 1 minus cosine squared. We know that's equal to sine squared. Although when you take the square root, you're going to get absolute value because the square root cannot be negative. Okay, so that will be the result of this. I'm going a bit fast here because all the elements were, of the calculation already introduced previously, including the transformation between the AI and the ZK, which is just the discrete Fourier transformation, and also the Bogriabov transformation, which is to get rid of the pair creation and annihilation terms. Question, Eric?
Yeah, I understand why we're throwing out the quadratic terms in the ZZ part, but why are we
dropping the
I get why we're dropping the quadratic terms. I don't get why we're treating AI and AI plus 1.
Oh, yeah. So that's a good one. Let's go through this a little bit slowly. So the linear terms, you basically will have a plus S AI dagger AI and a plus S AI plus 1 dagger AI plus 1, right? And then this whole thing is summed from I equals to 1 to n, right? Because the sum is periodic, and whether you are summing over AI or AI plus 1 doesn't really matter because we are basically just summing over all the lattice sites. Yeah, so they give you exactly the same thing. This is why I just put a factor of 2 here. That's it. Question, Kobe.
Didn't have the periodic boundary conditions.
That wouldn't, yeah. Without the periodic boundary condition, I also can't do this discrete Fourier transformation. Yeah. So the periodic boundary condition is always handy. And in this case, it doesn't introduce any complication because we don't have those phase operators. In the fermionic case, when we do Jordan-Wigner transformation, periodic boundary condition actually give us a headache, which is this boundary term that we have to look at the even number of fermions and versus the odd number of fermions. For bosons, we don't have this problem. Of course, the price you pay is this is only an approximation. This is only assuming that you're close enough to the ground state with all the spins pointing down or all the bosons in vacuum state. You have to be close to that state to make this accurate. Otherwise, this is not exact. But it's actually technically a lot simpler, so the mapping to bosons. So this is an energy spectrum you get. And I promise you that I'm going to show the experiment on this. So this is what we get, and we went through this in the last lecture as well. So the left one here is actually corresponding to the ferromagnetic case. They don't actually deal with directly a ferromagnetic chain, but it's effectively a ferromagnetic one. You can actually see the dispersion actually looks like a cosine, which is something we derived in the last lecture. And the right-hand side is actually a sine. So if you just look at the spectrum, just look at the color at the bottom, you clearly see it's a sine, and it's actually the an absolute value of a sine. Because if you do it symmetrically to the other side, it's just it goes like that. So that's exactly this expression we showed here. So it's basically given by a sine function 2 pi k over n. That's basically the momentum. So it's basically given by sine q, the absolute value of that. So it looks perfectly symmetric. So they showed the left the experiment and the right the theory, but you can see they agree pretty well. So it's basically a symmetric sine. It's an absolute value of the sine. So that agrees very well with the experiment. And this was actually sort of known many years ago, but there's this very nice neutron scattering experiment done relatively recently. So this paper is actually not that early. So it's a Nature Physics paper about 10 years ago. So only fairly recently people can measure this to very high accuracy. But previously there's some results on this as well to confirm the spin wave theory. And most of the experiment I showed you are a pretty good experiment, publishing high-level journals, so they should be quite trustable. Okay, so that means the theory is correct, and it's a relatively simple theory, but it works pretty well, at least for, so that experiment is for spin 1/2. So it's the simplest one, so for qubits or spin 1/2. So this works very well. Okay, so let's also try to understand this physically. So we know that this expression is more or less correct because it's verified by experimental measurements. So the first thing you notice is that if the momentum is very small, so let's basically rewrite this as our usual lattice momentum expression. It's simpler. So Q stands for the lattice momentum, which is equal to 2 pi k over n. So it basically varies from 0 to 2 pi. And we can see that it's actually linear when the q is very small. So it's approximately equal to just 2s times q. Right? So it's linear. So linear, again, means something that is corresponding to a massless excitation, because it's kind of like a photon, right? So the energy of these quasi-particles at low momentum is actually proportional to the momentum itself. So we only get this type of behavior when we have particles that are massless, like photons. They don't have a mass. So this is kind of more interesting because usually you will get excitation which looks like a particle with a mass. So these quadratic excitations are more interesting. But here we get these linear dispersions. So that's kind of similar to the weakly interacting bosons. We talk about the BEC, and we also find that the lower energy excitations have this linear dispersion relation. In that case, we actually talk about these continuous symmetry breaking. So here, unfortunately, you are not going to have continuous symmetry breaking, even though you have these linear dispersions. And this is actually at a quantum critical point as well. So later on, we're going to talk about that. In this one-dimensional case, this linear dispersion is actually pretty important because it tells you that there's an additional symmetry called conformal field symmetry here that gives you this linear dispersion. And this also means, in general, the energy gap between the ground state and the first excited state scales as 1 over n. So that part is always there. But this is, in 1D, this linear dispersion actually results from conformal field theory, which we'll talk a little bit more later on. But for now, this is just the calculation. This analytical calculation actually works well, at least for spin 1/2. It's verified by the experiments. Okay, so there's one thing I didn't actually talk about. That is, all of this is based on the approximation that the ground state is like this up-down state. But we know that that ground state is not accurate. So how can you get correct result even though your assumption is not necessarily accurate? So for this, we have to do some consistency check to see how wrong our assumption of the ground state is, right? So we can actually check this. So remember, the spin wave approximation basically requires that the AI dagger AI is much, much smaller than 1 or much, much smaller than S, right? Depending on, we're setting S to be 1/2, so it's not very different. So we're going to check whether this is actually correct. So we can actually calculate this. We can calculate the average number of bosons or the average number of spin excitations in the ground state, since we already have calculated this Hamiltonian analytically with the diagonalized Hamiltonian. So we can do this calculation similar to your homework problems. I think that's the last problem in your homework 3. It's a very similar type of problem. We're evaluating something like this in the ground state. And in this case, the ground state is actually, again, a vacuum state of the Bogdanov bosons. So this is evaluated in the ground state, which is basically a vacuum state of Bogdanov bosons. So it's a ground state of all the B's. So here, there's a little subtlety here. So the reason why I say it's a ground state because this energy spectrum is larger or equal than 0, right? And apparently the ground state should be, you can have all the, it should be empty, right? It should be a vacuum state for all the energy except for the k equals to 0 case, right? The k equals to 0 case is kind of a little bit of a trouble because in principle, the energy is 0 and you can put as many particles as you want in the ground state. But it turns out that this, 0 momentum case, the k equals to 0 case, is pathological. And the reason for that is if you look at the tanh 2 theta k, if you actually set this equals to 0, then you basically require the tanh 2 theta k to be equal to -1. And that actually can never be achieved with a finite theta k. So if you look at the tanh function, it looks like this, right? And the limit is 1 and -1. If you require the tanh of 2 theta k to be equal to -1, then the theta k has to be equal to -infinity. So this is kind of like a mathematical trouble. And usually the way people deal with it is to just assume that we don't include the k equals to 0 mode because it's not defined, it's ill-defined. So usually people just don't include this. And this is approximation anyway, so people usually don't care. And you just want to get some sense out of it. As we later show, this is actually at least partially wrong, but also partially correct because this part is verified experimentally. So we can just exclude the k equals to 0 case. So k to 0 excluded, which also means k equals to n is excluded. So this sum is only from 1 to n. But 0 is the same as n because it's periodic. So k equals to 0 or k equals to n excluded in the summation. Okay, so now we can calculate this. So this is going to be, so we can first change this to the momentum space. So this becomes ck dagger ck. So the a's goes to c first, right? So we first, map this to the momentum space. We get the c's. And then we also need to get back to the b's. So the C also gets mapped to B by the bulk-to-bulk transformation. So I'm not going to do this exercise again. And then you are going to basically apply these B operators on the vacuum state and then do the math here. So at the end of the day, this actually gives you something like this. So you actually get a sinh squared theta k. So this is sinh squared theta k, sum over this. And this is very different from that last problem in your homework 3. You should already finish it by now. I think most of you already submitted. So that last problem is actually a sine instead of a sinh because we're dealing with fermions. So in a lot of cases, if you're doing bulk-to-bulk, you might find that the main difference is for bosons you get hyperbolic functions. For fermions, you get trigonometric functions. So that's usually the main difference. Nothing too much. And then you can further simplify this. So I'm going to use some hyperbolic identities. So this is going to go to the following. And again, this is really just some math here. And this is going to be 2 pi k over n. And the reason is because theta k actually is defined by this thing. So theta k is like the arctangent of that cosine. So it looks a bit complicated. But mathematically, you can still simplify this. It goes to this with minus n over 2, constant shift. So the important part is basically this. So we need to evaluate this part. So actually, this is minus 1/2, not minus 1 over 2, because there's a 1 over n here. So the important part is the part in the in this bracket. We need to evaluate this sum in order to find the average number of bosons in the ground state. And if that one is much, much smaller than 1, that means the spin wave theory should be more or less correct, right? Because we make assumption, and then we calculate things and show that the assumption is pretty much valid. That's usually the way you do it. It's kind of like this self-consistency equation in the mean field theory. We have 2 homework problems in homework 3. So in the mean field theory, you also do something called the self-consistency check. So we're going to assume the Hamiltonian actually is given by this mean field. It's approximation. We're basically assume there's no entanglement or correlation of the spins. And later on, we're going to use this approximated Hamiltonian to calculate the magnetization. And it has to be equal to whatever assumed in the mean field. So this is very similar. It's a self-consistency check. If this whole integration actually gives you something that is much smaller than 1, then that means the spin wave theory is probably correct, or at least its approximation is good. So let's try to calculate this this summation here. So this is a summation, from 1 to n, and especially when n is large, we can actually convert this summation to an integral. So in the n goes to infinity case, we can rigorously convert this summation to an integral, and that is something you should have learned in calculus. So I'm just going to write the results here. So it should be 1 over pi and 0 to pi, and then the summation is sinh q dq. Also remove the absolute value because I'm only integrating over the positive half of it. Question, Bora?
What happened to the 1/2?
Where is the one? Yeah, I think the 1/2. Yeah, that's a good one. I think the 1/2 probably goes away because I'm only doing the summation from 0 to pi. So that one should be from 0 to 2 pi or from minus pi to pi. So there's a difference there. So here I'm only. So that one I put an absolute value because it can be negative. But this one I'm just removing that. So I'm basically just doing this integral here. And then the question is whether this integral actually converges or not. So I want you to think about whether this integral converges or not. So this is an integration of 1 over sinh q. And if you're not familiar with this, what the sinh function looks like, I can do a Taylor expansion for you. So this actually looks like q plus q cube plus something. So at least in the first order, when you do the Taylor expansion, when the q is very small, it's just linear in q. And the question is, do you think this will converge or not? So I'll give you a few choices. It should be simple enough. So A is converge, B is diverge, and C is you don't know. So I'm going to. This should be relatively simple, but I'll ask you a second question later on.
I think if you took it to infinity, monotonically,
Easily so much math.
Okay, so yeah, make sure you vote. It looks like we have a perfect tie between diverge or not diverge, converge or diverge. Okay, now it changes. Okay, even again. All right, that's tough. Okay, so all right. So the correct answer should be that this diverges because you actually got a pole here, so it's 1 over q. So when q is very small, so the part that causes divergence is actually near a very small q. So you are really trying to integrate a function that is 1 over x, right? So if you integrate over a function with anything that's finite, say over 1, so this is over pi, but it doesn't really matter. So it's a small part. You can make this even 0.1 if you want. If you integrate this is actually going to diverge because what you get is basically a log x, right? And then the log x, you basically evaluated it at 0 and at 0.1. The problem is the log 0 is actually infinity, right? So if you look at the log function, it goes like this, right? This is log x, right? So the log 0 is infinity, right? So log 0 is not defined. So this actually diverges. So it's also kind of, the other way to think about it is you're really just summing over the series of 1 over, n, when n goes from 1 to infinity. And we know this is a harmonic series, right? You're summing over 1 plus 1 half plus 1 over 3. And that doesn't actually converge. So here is more complicated. I use like a sinh, which could be more confusing. But what is really going on is that it basically just approximates to 1 over q, right? When the q is very small. It's just that part causes the divergence. So this actually goes to infinity. Unfortunately, this series does not converge. So this immediately means that the spin wave theory should be wrong, right? Because you're trying to calculate the average number of bosons in the ground state. Remember, the approximation requires this to be much smaller than 1. But what you actually calculate, this thing goes to infinity, right? So that means it should be very wrong. But it turns out that even though the sim sign is wrong, it only shows that the ground state cannot be this anti-ferromagnetic state. So this, this assumption we made in the beginning. So where is the picture I draw? Yeah. So this near-ordered ground state just shouldn't be correct, right? Because if that's the case, then you should get a finite number of excitations, but you don't. You get infinity. And that's correct. We know that this is not the ground state. We even show this sort of, the correct one is like it's up, down, but gets twisted down. So the correlation is actually decay. So that's consistent with the fact that this cannot be right? But on the other hand, we also just show that this expression is more or less correct, right? So this sign dispersion spectrum, because it's more or less verified by the experiment. So the way to think about this, why it's kind of halfly correct, halfly wrong, is even though this goes to infinity, but the speed of its divergence is actually very slow because I'm changing this to integral by setting n goes to infinity. But if you actually calculate the sum, it kind of diverges only as a log n, and the reason is really just because here, right? So if you look at something like this harmonic series and you only sum to capital N, and this approximately is proportional to log n. So it's a very slow divergence. So even though it diverges, but it's kind of slow. And this is actually unique to 1D. You only get this log n divergence. So that means, at least for a finite system, it's not completely wrong, right? If the n is not very large, you still get pretty much a finite number. Yes, it's certainly not much smaller than 1, but it's also not really infinity. So it's only going to infinity when the n is huge, right? So even if you have 10 to the 23 particles, like in the real material, log n is only 23, right? If you take the log with a basis of 10. So it's actually not that bad. So that is kind of the reason that this result is halfly correct, because it still captures some information of the ground state. This divergence is not too bad. So that's usually the case. As long as what you find the average number of bosons is not infinity, it's not really like a very large number, then the spin wave theory should be correct more or less. Of course, if it's much, much smaller than 1, like in the ferromagnetic case, it's pretty much exact. And this is something in the homework of homework 5 you are going to, in the homework 4 I already assigned, you are going to deal with. So later on, if I have time, I can briefly talk about it. So there's a problem where I ask you to calculate the energy spectrum in the ferromagnetic case. You are going to find the spin wave theory is basically exact. And then you'll also be asked to calculate this anti-ferromagnetic case. You can do exact calculation on the energy spectrum by just diagonalizing the Hamiltonian. You're going to find in this case it's not, they don't actually match perfectly. There's some difference, but the difference kind of gets not too bad as when n is large. So it's kind of the same trend. So this is what's going on here. It's qualitatively correct, but it's definitely not quantitatively correct. Okay, so this is the case for 1D. And now I'm going to ask you another question. So this is in 1 dimension. So what about 2D or 3D? So you can also do the same calculation here. The good thing for the spin wave is you don't need to care about these non-local phase operator in the Jordan-Wigner. So you can actually do it in arbitrary dimension. The only thing you need to do is to map, right? So these SIs and SJs to A and A dag and A, and it doesn't really matter if this 1D or 2D structure. You can also do it for long-range interacting system. It doesn't really matter. You can do this mapping directly, and at the end of the day, if in 2D, so this integration is actually going to change to something like instead of integration over Q, you're going to integrate over the length of the momentum. So it's something like a Qx squared plus Qy squared. And then you're going to do an integration over both dqx and dqy. So you're always going to integrate over some function, a sinh of the momentum. And the momentum in 2D, it's the magnitude of the momentum. So it goes like Qx squared plus Qy squared. And then you're integrating over both momentum in x and momentum in y. So now my question is, will this one actually converge or diverge? So again, 3 choices. I'm not going to write it down. A for converge, B for diverge, C for you don't know. So I'm going to open another question here, and you can think about it. So what if this integration is over 2 dimensions? This is a pure mathematical question, but it's interesting to think about it. So again, for simplicity, you can forget about the sinh, because at small momentum is basically approximated by just 1 over Qx squared plus Qy squared. It's kind of the magnitude of the momentum. Do you think it converge or diverge? A for converge, B for diverge. Don't get it wrong. So A for converge, B for diverge. C for you don't know. So it's in 2D.
It's conceivable that it does. I just don't remember this particular one.
This should be a problem you study in calculus. Maybe you all forget. But that's a good check of whether you still remember calculus.
So it's at least
Series is like kind of the boundary between divergent series, right? And so I think
Okay, it looks like we get a tie again. Oh, actually the tie is broken. Okay. Still pretty close between diverge and converge. I don't know who choose D. There's no such option. Okay, so yeah, so the answer for this case is actually it converges. So A is the correct answer. So why is that the case? So this should be something you learn in calculus, like how you do 2-dimensional integrations. In this case, you can actually use the polar coordinate. So you can see this square root is kind of ugly, but you can just call it 1 over r, right? So r, if you have x and y, what is square root of Qx squared plus Qy squared is really basically the the distance of this point. Basically the length of the momentum, right? So it's basically the radius. So if you do that, then you're actually doing a 1 over r. And here, of course, you can't actually do the integration over x and y. So instead, this actually becomes r dr d theta. So this is kind of like the Jacobian. And the way to think about it is, if you do an integration in the polar coordinate, so the unit you're looking at is something like this, right? So it's kind of this area, shaded area. So this is your d theta. So this is the polar angle. So it's an angle, and this is your dr. So this line is your dr. And you need to calculate the area of this, because integration is kind of like a summing over the area. So if you do a simple math here, so this area is equal to, r squared d theta. I think it's d theta over 2. So that's basically the area of this little, little angle here. And then you also have r plus dr squared d theta over 2. So you're looking at the difference of this. This actually gives you r dr d theta. Right? So the way to calculate this shaded area is to calculate 2 slices of the pie, right? So it's like 2 slices. If you do that, you actually get r dr, and this r perfectly cancels with the 1 over r. So at the end of the day, you are just doing an integration. I think it's kind of like from 0 over pi, and then another 0 over 2 pi, then dr d theta. So this, of course, is going to converge to some finite number. So there's no divergence. In 2D, this 1 over r actually gets canceled by the integration in polar coordinates. So that's a way to think about it. And actually, this is true. So in two dimensions, the spin wave actually works. And there's an important physical consequence is that in 2D, if you take the same antiferromagnetic Heisenberg model, like in a square lattice, actually at 0 temperature, the ground state does have this antiferromagnetic order of this up, down, up, down, up, down. The order is definitely there, but there's a long debate whether this order actually exists, because nobody can actually cool this to 0 temperature. If the temperature is finite, people actually find there's no magnetization, there's no antiferromagnetic order. It turns out that the temperature has to be extremely close to 0 in order to actually see this antiferromagnetic order. And this is actually verified by quantum Monte Carlo calculations. So I'm not going to talk about that, but there's actually a long debate in the condensed matter physics about whether in 2D you can actually have that up down state, in the ground state. And it turns out yes. So the spin wave theory actually gives a correct prediction. In 3D, everybody knows that at 0 temperature you should have the order, and that's actually we have some 3-dimensional materials which are antiferromagnetic, and people actually measure the magnetization there. So it does make sense. So 3D, even finite temperature, you can have that order. So that's kind of the success of the spin wave theory. It's actually a pretty commonly used tool in condensed matter physics and many-body physics. So actually, I want to show you one of my own papers that uses spin wave theory. Just want you to show that this is a pretty useful techniques. So again, this is an experiment done by Chris Monroe's group. Let me see if I can download this paper. Where is the download button? Or maybe there's not, but at least I can just scroll this down. So actually, I was in charge of the theory of this paper. So the Hamiltonian is actually something similar to what we're dealing with. Not quite similar, but something we dealt with before. So it's a long-range transverse field Ising model. And this one, you can't actually use Jordan-Wigner transformation. So I want to do some theory to predict the dynamics. I'm not going to talk about the details, but hopefully this one shows the way I deal with this. Actually, it's probably in the supplemental material. That's the unfortunate fate of theorists. Most of the stuff goes to the supplement for the experiment, for experimental work. So let me download this. Okay. Yes. Okay, so I basically write this part. So this is a Hamiltonian. This is transverse field Ising Hamiltonian. I actually just map this via this constant and Primakov transformation. It works for long-range interacting system as well. So it gets mapped to this Hamiltonian, which you're kind of already familiar with. There are these hopping terms, and also these pair creation and annihilation terms. And you can basically just do additional calculation here. You can see that actually, sort of first map it to the momentum space, these CKs and CK daggers, very familiar. And then I also did the Bogdanov transformation there. And at the end of the day, I can basically find the energy spectrum. In this case, it looks like this. Right? You can also see the tangent here. So it's kind of similar to what we're doing. But there are, of course, other stuff that we haven't covered yet. So they're talking about this, density matrix here. I'm not going to talk about the details, but this is like a basic technique you can actually be used, towards your research. And this is actually published in a pretty high-level paper. It's a subjournal of science. All these calculations matches with the experiment very well. So if you actually see there are some curves here, I think it's these curves here. So there's kind of like a theory, there's an experiment. So they actually, don't differ too much. So you can see that there's these guidelines. Experimental data have some fluctuations there, but it's more or less correct. Okay, so that just shows you that this is not something that is just purely, in the textbook, but it's actually something you can use in research and even in, cutting-edge ones. Okay, so that's pretty much about this, mapping to bosons and how we do this spin wave approximation. So the only thing you need to keep in mind is that, you have to make sure you're talking about a state very close to that polarized state you're starting with. So that spin wave approximation is the only catch. Otherwise, it's actually a relatively easy transformation. And in the last problem you have a homework for, you're going to deal with kind of a very similar model to this. The only difference is, I can briefly talk about it. So we actually add a coefficient for the ZZ. So the ZZ interaction is not 1, so I call the coefficient delta. And I want you to basically repeat my whole calculation, try to calculate the energy spectrum and do all these, mapping to bosons and join a weak the Holstein-Primakov transformation. It should be relatively straightforward, but it's a good exercise for you to know how to do this whole, calculation. Okay, any questions? Okay, so we're done with the calculation. So now for the concept. So today I want to introduce another important concept. It's called the Haldane's conjecture, and this one is also related to a Nobel Prize. So Haldane is a professor at Princeton, and he actually got the Nobel Prize about, I think it's about, I forgot exactly, I think 2016, it's about 7 years ago. I think one of the reason he got the Nobel Prize is actually because of this conjecture. It's actually closely related to what we're talking about here. So we just said that this spin wave theory works kind of partially correct for the spin 1/2 systems, right? At least this is verified experimentally. For example, this. So this energy spectrum is already measured experimentally. There are actually some old experiments done in the 1980s that already verify this. Not to that beautiful plot I showed you in the Nature Physics paper 10 years ago. But this is already known. And everybody was happy, think that the spin wave theory at least give you the qualitative correct answer. But Haldane actually think maybe not. So if you look at this expression, there's an S there, which is basically the length of the spin angular momentum, right? So in principle, this theory works not only for spin 1/2, but also works for spin 1, for spin 3/2, spin 2, etc., right? And in some materials, there are indeed spin 1 particles interacting. For example, if you have 2 electrons in your valence, in your outer shell of the atoms, you could actually get a spin 1 or a spin 3/2. So there's actually potentially a way you can test this for different materials. But most materials have spin 1/2, right? It's just an electron spin in the outer shell. But Haldane basically says that, so yes, so this theory works well, but he thinks that this only works well when the S is half integer. So Haldane's conjecture basically says that if you think about this antiferromagnetic Heisenberg chain, it's this model we are talking about. So again, I'm going to write this Hamiltonian, Si dot Si plus 1. So it's just this simple Hamiltonian. But he actually thinks that the ground state of this Hamiltonian is not the same for S being half integer versus S being integer. And that is something completely mind-blowing at his age. He basically proposed this in the 1980s, something like 50 years ago. People already did experiment on the spin 1/2 and verified it. And the other thing is for the spin 1/2, we also know that there's this exact solution. It's called the beta ansatz. Beta is a physicist got the Nobel Prize because of that. He exactly solved it. It also agrees with the spin wave theory, which is agnostic to the actual value of the S. So everybody thought with the exact solution and the spin wave theory, we're all set on this problem. But Haldane basically says no, we're not all set. The half integer and the integer case are actually different. But nobody could actually find an integer spin chain experimentally, so it kind of becomes only a conjecture back in the 1980s. He was actually getting a hard time publishing his paper, and later on I'm going to show you a part of his Nobel Prize lecture. He actually went through this. It was quite an interesting story. But it turns out later on that his conjecture is totally correct. So I want to first mention a little bit more about his conjecture. So what is the main difference of these two? So for the half integer, because there's the exact solution, and which also agrees with the spin wave, so we know what's going on. So basically we have, so first we know that the energy gap goes as 1 over n, so it's actually gapless. So basically there's, in the large n limit, the ground state, first excited state, the energy difference all goes to 0. And then you can also calculate the correlations. The correlation actually decays as a power law. So this is also something we went, from that, Nature Physics paper. If you look at something like Sij, Szj, and with this difference of I minus j, this actually approximately is equal to -1 to the I minus j divided by the distance of I minus j. So it kind of alternates, but also decays as this 1 over distance. So that's kind of the twist I was talking about. So you get this power law decay. So that's the main signature. So this is already verified experimentally. So Haldane is okay with that. But he's saying that for integer ones, it's going to be fundamentally different. So first, the system actually has an energy gap. So the ground state and the first excited state, the energy actually doesn't go to 0 when the n is infinite. No matter how large the n is, there's a finite energy gap. So that's the first thing. And the other thing is, if you look at SIZ, SJZ, how they decay, it should decay exponentially instead of this power law. So with some maybe some coefficient, I call it C, which doesn't matter, but it's an exponential decay. So that is fundamentally different from the top one. And at that time, nobody believes him. But later on, I think in the 1990s and towards 2000, there's this very powerful technique called DMRG that can actually solve a one-dimensional spin chain with up to like 200 or 300 spins. So you can actually test which one is correct. And it turns out that Haldane is correct. So this DMRG calculation in the modern age is also called the matrix product state calculation. We're going to have a separate topic talking about that, and also give you some hands-on experience with some software library that's already out there. But today we're not going to talk about that, but basically say, yeah, I just want to say that Haldane's conjecture is actually correct. So this is pretty remarkable, because at his age, he can't even do the simulation for more than 10 spins on the computer back in 1980s. But he basically conjectured that it has to be this case. And after 10, 20 years, people actually verify this. So of course, Haldane is not conjectured this based on nothing. So he has a pretty deep understanding of the of quantum field theory. So the way he come up with this conjecture is he actually first tried to understand the spin model by mapping it by doing some kind of quantum field theory. And there's a particular formalism called for this. If you want to map your spin models to like a field theory model, there's a technique called coherent state spin integral. So coherent state spin path integral. So this is of course based on the Feynman's formalism of quantum mechanics, which is based on path integrals. So this is not within the scope of this course. If you're interested, you can take the graduate quantum mechanics here, the 520 and 520 on. They're actually going to teach path integrals and quantum field theory. But I just want to show you sort of like the very high level idea of why the two actually is different. So you can do this thing called coherent spin state path integral. By the way, this is actually in the Sachdev's book. So in Sachdev's quantum phase transition book, you can actually look at chapter 19.3.2. So it's pretty late in the chapter, so it's a pretty advanced topic. I'm definitely not going to cover it in details. But at the end of the day, what he finds is that when you do this path integral, the half integer spin and the integer spin actually are fundamentally different. And that reason, you can actually understand it. So I'm going to ask you a simple question. So if I have just a spin 1/2, which is a qubit, right? Suppose the I start with the qubit pointing in the opposite direction, so that's a 0 state. And then I'm going to rotate this qubit by 2 pi on the Bloch sphere. So basically take that arrow and then rotate it by 2 pi. So it goes back to the up. Do you think the wave function goes back to itself, or it goes to the negative of itself? So to help you, I want to write down what the state looks like for a qubit on the Bloch sphere. So it's actually given by cosine theta over 2 of 0 plus sine theta over 2 e to the I phi 1. And the question is, I'm going to rotate theta by 2 pi, right? Theta is the angle I made with the z-axis. So this is x, y, z. So that should be relatively simple. If I just change theta to theta plus 2 pi, what will the state look like? Does it go back to itself, or it's equal to the negative 1 of that? So look at the theta over 2 here. Key is the theta over 2 here. Yeah, see that? There's a theta over 2. And for a long time, when I first learned the Bloch sphere and this representation, I was always wondering, why do you have a theta over 2 instead of just theta, right? And if you do every calculation, it shows you it has to be theta over 2. Because if you calculate sigma x, sigma y, sigma z, theta over 2 makes sure this mapping is correct, right? For example, if I calculate sigma x using this, you're actually going to show that it's equal to like a cosine theta, cosine phi. So that's the projection of that, of the unit vector onto the x, y, z plane. So it has to be theta over 2. I was always wondering why there's a factor of 2. Yeah, mathematically it makes sense. But it turns out that one of the most important things is the theta over 2 makes it that if you rotate this by 2 pi, you actually get a minus sign because you get a cosine pi and a sine pi, right? So it's actually a negative one with a trigonometric identity. The sine x plus pi is equal to minus of sine of x, and similar for cosine. So you actually get the negative one. So the psi actually goes to the negative of psi. So that is kind of unique for spin half integer. We don't talk about spin 1 on the Bloch sphere. That's kind of a different story. But it turns out that for integer spins, you can start with spin 1. If you do this rotation, it just goes back to itself. And you could also say that this is something related to the bosons and fermions, right? Because the spin half integers, they're kind of like bosons, and you get this -1 phase. And for the for the bosons, for the integer spins, you don't have it. And Haldane is basically making advantage of this difference. So if you do this coherence path integral, it actually has to deal with like an integration over the theta for 2 pi. And in one case, you get a -1. In the other case, you don't. And that -1 is actually is very important. And we all know that the importance of -1 just looking at the difference between bosons and fermions. And because of that, he basically predict that the integer spins should be completely different from the half integer spins. And that later on leads to this conjecture. Okay, so he basically just stops here, but this is not the end of the story. So it turns out that for these integer spins, the case that you can actually have an energy gap, and also this exponentially decaying correlations leads to something that is discovered many years later. So this actually, leads to a completely new type of phase. It's called the symmetry protected topological phase. It's a pretty long name. So we're going to talk about this in more details later on when we're talking about the classification of different quantum phases, the role of entanglement, as well as these matrix product state. And we're going to have some more detailed examples here. But here I just want to mention the concept. So this actually belongs to a new type of matter called symmetry protected topological phase. And these ones are, they're very common now. It's been a really hot topic in condensed matter, at least maybe 5 or 6 years ago. So this very important concept called topological insulator is actually a symmetry protected topological phases of matter. So there are different symmetries there. In this Haldane, in this antiferromagnetic Heisenberg model, there are some symmetries there that protect this this particular ground state's behavior. Okay, so I want to show you this video I mentioned. So this is actually the Nobel Prize lecture in 2016. So I'm just going to show you the last part about this quantum part. See, hopefully this is muted. So I actually had the chance to meet with him in person when I was at a school in Princeton. I was a PhD student by then, and he's actually a very modest man, so he's very polite. So I really like him. Okay, so.
This was a very obscure, a difficult piece of work, and no one knew how to calculate anything else except energy levels from it. But in the mid-1970s, another piece of work, a remarkable piece of work, going back to the 30s, a Jordan-Wigner transformation, which maps spins, which are bosons really, to fermions by relating spin up to be filled and spin down to be empty states. Gave a way to translate these spin chain languages into fermion language. And this actually was a lot easier to do calculations with than the beta ansatz, and it allowed one to translate things into calculations you could do. And I guess progress always happens when you can actually turn something to some calculation you can actually do on a piece of paper or understand. Then you can understand all the details. And this was done by Luther and Peschel. Luther was at Nordita for a long time after that. And they turned this thing into a fermion problem. And to cut a long story short, they got most of it right, but they missed out some detail, which I discovered later by applying this Luttinger liquid theory that was mentioned. And I found that that they didn't really have an understanding of what happened when you went from an easy axis to an easy plane to easy axis antiferromagnet, whether the spins were in the plane or were either point out of the plane. And looking at the numerical, this new tool gave us a thing to extract numbers from the beta ansatz calculation. They showed immediately some term was missing. And these pictures here are actually exactly the quantum translation of the Kostler-Fowler story that Michael will tell you about. So it turned out that the spin half system was special rather than the spin one system. They both were Kostler-Fowler transitions, were driving you from easy plane to easy axis, but there was a special cancellation effect, which I guess we'll maybe say here. between in the spin half case. Here that you've translated what Mike's going to tell you about from a two-dimensional space to a space-time diagram, and here there's a tunneling process that takes you between a configuration where these are compass needles in the plane. They kind of stay in the plane, and as you go around, there's periodic boundary conditions. You go around. In the first case, there's no kind of winding number. The second case, there's a twist hook on it, like a Mobius strip or something. The twist went in, and
So he explained this in a much more complicated way, but this twist is kind of related to that -1 I was talking about.
you can't get from those two things continuously. You have to do some kind of breakdown, and there's a tunneling point, which is a vortex. And it turned out that for the spin half case, you only got a double vortex because if you have to do this process of tunneling on one of the bonds between the spins, and if you look at the process on two neighboring bonds, everything should be identical if the bonds were identical strength, except the two paths, in one path, one of the spins rotated 180 degrees clockwise, and the other one is rotated 180 degrees anti-clockwise, so the difference of the paths is rotating a single spin 360 degrees, but if it's a half integer spin, you get a -1 factor. So the quantum mechanics told you something. So looking at this way gave you a completely new way to look at things, and it turned out that the conventional wisdom was completely wrong. And finally, so we came up with this new story which shocked people at the time because it conflicted with preconceived notions based on the beta ansatz equation seemed to confirm incorrect ideas about spin waves. And finally, let's not go through this too much, but at the end of the day, this turned out, this new state of with this.
So this one, we're going to talk about this in more details later on.
Integer spin liquid state that I found turned out to be one of the simplest topological states with a very non-trivial entanglement. They're a spin 1 system, and the interesting thing is the spin 1 can be viewed as two spin halves glued together. And in the usual case, they just point in some direction, but here the spin 1 again splits, fractionalizes into two spin halves, which one on either side, and they grab onto the spin 1 half from the partner, and the next one along, and get entangled into a singlet state. And when you do that, you get left the two spins at the end of the chain. They get left with one arm stretched out here.
So this is actually very close to the Majorana fermions we talk about for the spin 1 half. You get this half of the fermion at the end, which gives you this topological order. In this case, it's kind of very similar. Instead, we actually have spin 1, and then they get fractionized at the end. You get spin 1 halves at the end, which actually are free and gives you this topological order. So we're going to talk about that later.
The other arm stretched out here, so there's like two half spins at the end. This is two unexpected spin 1 halves at the end of the thing, and this is precisely the analog of the edge states in the quantum Hall state. Again, this feature you find in all the topological states, that there's something strange happening at the boundary where the edges are, where things go from into normal. So anyway, so that brings me to basically the end of the story. I couldn't really give you all the technical details, and it's probably quite confusing because it's very difficult to explain this to a general audience, even a general audience of scientists if they're not condensed matter physicists. And but basically, my opinion, my interpretation of why this prize was awarded now is because so much has suddenly in the last 10 years has come out of all this old stuff. These various little findings, which in each turn came from people finding something more amazing than they were looking for, just they noticed something strange, and it gave you a new way of looking at things. And what's happened is that we've over my lifetime in condensed matter physics, I've seen that the kind of things we were taught and learned from textbooks like Ashcroft and Mermin and things back in the 70s, a lot of the details that were thought to be really important then, and really we put them away as boring stuff which doesn't relate, not important, and all kinds of new things like entanglement and new ideas which were not present in any of this old stuff have become the central kind of questions that we're struggling with. And after the topological material started to be found concretely as real things, there was also proposals that they could be used as a so-called platform for topological quantum information processing, and that of course has stimulated a large amount of interest, and there's been a huge amount of people with cold atoms, quantum information, condensed matter. Even the string theorist Ed Witten is now devoting part of his time. I guess string theory is, there's some spare time out to deal with other things now, and they're getting very interested in extending all this topology to 4 dimensions. So we now have tables of topological matter up to 8 dimensions. So you can see how the influence from outside the field has influenced things. But this is a very exciting area because we're finding all kinds of what I consider neat stuff about quantum mechanics that we didn't know before. And there seems to be plenty of new insights to gain. So when you can find something very simple and beautiful, we all think that's the truth, and maybe we're going to learn a lot about matter and learn a lot about possibly applications of it. Thank you.
Yeah, I like what he said, right? Yeah, if it's simple and beautiful, then it's probably good science. Yeah. And it's like, as in the Haldane's conjecture, it's actually a pretty simple conjecture, but it turns out there's something very deep about it, and that starts all the field, all these research on topological materials. Okay, so I have about 5 minutes left, so I'm going to give you some hints on the homework. So let me switch back to this. So and you can start working on that this week. So for the problem 1, this is actually called an XY model. So you have the flip-flop and the plus minus and minus plus term. You can also rewrite them as, I think it's a half of XX and YY, sigma x plus sigma y, the equivalent. And what I ask you to do is to basically find the energy spectrum of this model, Y the Jordan-Wigner transformation, and also basically underline the lecture note here. So this is for lecture 12. You can look at the Jordan-Wigner transformation, and this allows you to map this sigma plus sigma minus to C dagger and C. And the basic rule is the nearest neighbor, then there's no phase operator. So the sigma plus I, sigma I minus 1, sigma minus I plus 1 just map to the Ci dagger, Ci plus 1. So this is something we already deal with. And the only caveat here is that we have a periodic boundary condition. Right? So the periodic boundary condition is because the sum is from 1 to n. So the sigma n plus 1 is the same as sigma 1. And to give you a sort of a quick hint here, so with the periodic boundary condition, the problem is that if you have terms like sigma, n plus 1, dagger, and sigma 1 minus, something like this, sorry, sigma n, not sigma n plus 1, sigma n plus and sigma 1 minus, because 1 is the same as n plus 1. Then when you do the Jordan-Wigner transformation, this one actually goes to Cn dagger, C1 minus, but there's a phase operator, which is equal to the minus 1 to the power of total number of fermions. So this is something in lecture note 12, but I'm just writing it here. And this is kind of the nuance here. If it's without this sort of phase operator, then it's just a perfect quadratic model. You can diagonalize it. But with this, you basically need to look at 2 different cases. One is that the n total is even, and the other case when n total is odd. Right? So if you look at 2 different cases. What it means is your Hilbert space, the entire Hilbert space, is split into 2 subspaces. One is that you have even total number of fermions. The other one is you have odd total number of fermions. So for the even case, this minus 1 phase is gone. For the odd case, you get a minus 1. So and it turns out that this is going to basically change the boundary condition. So in the even case, the boundary is just C1 equals to Cn plus 1 is equal to C1. And for the odd case, it actually means Cn plus 1 is equal to negative of C1. I might get the opposite, so, but this is a basic idea. I might get these 2 cases, swapped, and then you can just basically go back to your Hamiltonian because you get this Hamiltonian H once you get mapped, so it just becomes Ci dagger, Ci plus 1, right? And then you have some terms from the magnetic field, which I can't remember exactly what this is, maybe 2 times H Ci, something like this. And then you can diagonalize this through the discrete Fourier transformation. And this 2 boundary condition will basically, correspond to the case where k is, an integer or a half integer. So again, that's very similar to what we have in the class. But this is actually simpler because you don't need to do the Bogart-Bov transformation. The Hamiltonian does not contain any pair creation and annihilation term. So just introducing the discrete Fourier transformation with that boundary condition nuance, you should be able to solve this problem. So the second part is for diagonalizing the Hamiltonian with this, with this discrete Fourier transformation. And third part is to calculate the ground state energy. And again, the ground state should be basically a vacuum state for the for those fermions, because you are going to show the energy spectrum is positive or is non-negative. So you can find the ground state, and there are two different cases. One is for h larger than 1, because there's an h that appears in the Hamiltonian. It's kind of like a chemical potential term in the fermionic picture. So you're going to get this, and then you're going to show that they're actually different. In one case, the system is gapped. In the other case, when the h is between 0 and 1, you actually will find the energy gap. So basically, it's the ground state and the first excited state goes to 0. So, and this basically indicates this phase transition, because the energy difference goes from 0 to a finite. So that's where the phase transition happens at h equals to 1. So that's a real quantum phase transition. And this is the exact treatment of this Hamiltonian. So there's no approximation made. So that is for this first question. For the second question, I kind of briefly mentioned in the lecture already. So we're dealing with this spin 1/2 ferromagnetic Heisenberg chain. The minus sign in front denotes the ferromagnetic interaction. And we're also assuming these are spin 1/2 particles. So the first one is find the ground state energy of this Hamiltonian. So this you can find analytically because it's a ferromagnetic Hamiltonian. So the ground state is all the space pointing in one direction. And it doesn't really matter what direction it's pointing because it's all degenerate. Right? You have this symmetry there. So you can just assume all the spins are pointing in z and then just calculate the energy. So that should be relatively straightforward. And the second one is to write a numerical code that does this calculation. So if you write a numerical code, this dot product consists of xx, yy, and zz. So you can find the angular momentum. So these operators are all made of Pauli matrices. You should be able to write this numerically. And then you can basically compare with that calculation you did in part 1. So the only sort of caveat here is you need to write the Hamiltonian as a sparse matrix. So remember, this is kind of similar to one of the earlier homework problems. You need to first write a tensor product of these angular momentum operators with identity on the other sides. But at the end of the day, once you have the Hamiltonian, you should convert it to the sparse matrix. So there are commands in different software. In MATLAB, you just do a sparse, with the parentheses of the matrix, and convert it to the sparse matrix. Otherwise, it will be very hard to calculate the eigenvalue problem of a full matrix up to 12 qubits. So the Hilbert space dimension will be 2 to the 12, which is about 4,000. You can still do a full diagonalization, but it's going to probably take maybe 20 minutes, 30 minutes, or if you have a really poor computer, it could take hours. But once you convert it to a sparse matrix, this software can actually use some different routines. It's called the Langsos algorithm to calculate the ground state energy, and that takes it should take just a few seconds, or at most a few minutes if you have a bad computer. So just make sure you do that. And in principle, you can even write the Hamiltonian as a sparse matrix. But at least you should be able to write it as an ordinary matrix and convert it to the sparse matrix before you calculate the eigenvalues. So I'm running out of time. I'll talk more about this at the beginning of the next lecture. All right, I'll see you on Wednesday then.